Yeah, so thank you for the introduction and thank you everyone for being here. I'm Paolo Erdman. I'm a postdoc at the Freie Universität, and I'll be talking about how we've been using in the last few years reinforcement learning methods in quantum thermodynamics. And this work was done together with my supervisor, Frank Noé. And some of this work was also done in collaboration with people at the University of Geneva, in particular, Paolo Abiuso, Alberto Rolandi, and Martí Perarnau-Lobet. So arguably one of the most maybe interesting conceptual and practical applications of thermodynamics is that of heat engines. So I will focus in this presentation on driven thermal machines. So as you all know, from an abstract point of view, we'll consider some system that can be coupled in time to a hot bath and we can exchange some heat. We can couple it to a cold bath and exchange some heat. And importantly, we have a set of time-dependent controls that allow us to control the state of the system and to exchange work with it. So for example, if this control is the position of the piston, by acting on the control, we can exchange work. And in particular, I would then consider the heat engine application where we want to extract work from a temperature difference, and the refrigerator where the aim is to extract heat from a cold bath by putting work into the system. And of course, since this is a quantum thermodynamics conference, we'll replace the classical system with some open quantum system. And the control will be some local control on the quantum system. For example, a magnetic field or gate voltage controlling, for example, the level splitting of a qubit or a quantum dot. And in this presentation, I'll focus on using the Limelight equation. So we'll describe the dynamics of the reduced density matrix of our quantum system through the Limelight equation, which depends explicitly on our time-dependent controls. Now, let's say we have an assigned control or an assigned cycle. The performance is mainly characterized of a heat engine by the power, which is simply the work over time, or by its efficiency, which is the work we extract divided by the input heat. Or instead of maximizing the efficiency, we could also think of minimizing the entropy production. And another quantity is also power fluctuations, which we quantify as the variance of the work distribution divided by time. And what we want to answer in this presentation is which functions UDT, so which type of cycle maximizes these quantities. And as we've nicely seen in the previous slide by BJ, there's a trade-off between these three quantities, so we cannot simultaneously optimize them. This is, for example, also nicely shown by the thermodynamic uncertainty relations here derived for steady-state engines. So essentially what this is telling us is if we want to have a high power, for example, we either need low efficiency or high power fluctuation, so on. So the way we tackle this optimization problem is to use a concept of Pareto optimality. So essentially we search for those collection of cycles where you cannot further improve one quantity, for example, the power, without sacrificing another one. And under certain assumptions, this can mathematically be done by searching for the cycles that optimize this figure of merit F, which is simply a linear combination of our three objectives. So here we want, for example, a high power, low power fluctuations, and low entropy production. And if we repeat this optimization for many values of these coefficients A, B, and C, which are just numbers between 0 and 1, that's sum to 1, we can find, under some assumptions, all of these Pareto optimal cycles. So there have been many approaches in literature to find cycles that optimize the performance of heat engines. For example, one approach is to fix the structure of the cycle like Otto cycles and optimize it over certain parameters of these cycles, like the period, for example. Or people have studied the so-called slow or fast driving regime, where the speed of the driving is compared as slow or fast with respect to the thermalization timescale of the quantum system. Or another approach is to take cycles that work well in the adiabatic regime and to consider them in finite time using, for example, shortcuts to adiabaticity. And also variational approaches have been proposed. But arguably, all of these methods, aside from variational approaches, do not guarantee that we will actually find the optimal cycle. So what we did, we wanted to develop a numerical method such that we can find optimal cycles without making any assumption on the structure of the cycle, nor on the speed of the driving. In principle, this method could be applied even to experimental devices of which we do not have knowledge of the underlying model. It's also a framework that allows to handle noise in the control quite naturally. And it's been also used recently to reduce the entropy production in closed quantum systems. And as another motivation, these are, for example, the percentage of papers in physics, chemistry, and material science that use machine learning methods. And as we see, they've been increasing quite rapidly in the last 5 to 7 years. And even specifically in the quantum physics community, there have been many applications, but arguably there haven't been many applications of it in the field of quantum thermodynamics, with the exception of a few papers, among which this one. So the idea here was to use reinforcement learning for this problem. And reinforcement learning is a mathematical framework that allows us to solve optimization problems that are formulated in this way. So a computer agent has to master some task by repeatedly interacting with some environment. So we take time and we discretize in small time steps. And in every time step, we allow the agent to choose an action, which consists of what is the value of the control U that we pass to the engine, and then it will be kept constant for some short time dt. And we additionally allow it to choose a discrete action D, which corresponds to whether we want to couple the system to the hot bath, to the cold bath, or to just a unitary evolution. And this is motivated by typical cycles where you have a hot stroke, a cold stroke, and so on. But we allow this to do it at every single time step dt. And then as reward, let's say as feedback to the agent, we choose, for example, in the power optimization case, we return what is the average power that was delivered in time step dt. But since the aim of reinforcement learning is to learn how to choose these actions as to maximize the sum of the future rewards, we will end up optimizing the average power over some long time scale, capital P, which depends on this factor gamma. This gamma is known as a discount factor in reinforcement learning. It's essentially a number between 0 and 1. And if you choose this close enough to 1, we see that we're really optimizing the power over a long time scale. So we first applied it to arguably the most simple model of a heat engine, so simply a two-level system where our control is simply the level splitting of the qubit of the two-level system. And what we find, so here we show the power of the engine as a function of this step, training step. So each step is one single dt evolution. So this is not a full cycle, but it's just a single dt evolution. And these are the actions U, so the control, as a function of time that was chosen by the method, zoomed in around these 3 points during training. So we see that at the beginning, the action, so the control U as a function of time is completely random. Here, the color corresponds to that discrete action, hot bath, cold bath, or unitary. And you see that the power is negative. But as time goes on, the power increases, and in the end, we converge to a cycle which is simply given by the square wave. And in this paper, we showed that in the specific model, we proved analytically that this is indeed the best cycle for power optimization. So then we move to a case where we do not know the optimal solution. And this is a model of a refrigerator based on a superconducting qubit. So here in the center, we have a superconducting qubit, and the aim is to refrigerate this resistor. And here we have control over the sigma z term, but not over the sigma x of the qubit. So essentially here, the Hamiltonian doesn't commute at different times. And this is, it's a model of this device that was studied experimentally in the group of Yuka Pekola. And here we show, again, what is the cooling power, P of R, as a function of step. It reaches a maximum value, which corresponds to this black thick line control. So we compared it here to what was proposed in literature, which was this dashed line driving. So this is, again, the control as a function of time. And we see that we find a substantially larger cooling power in this case. And here we could show that this kind of additional strange jump that was found by the method actually mitigates this detrimental effect known as quantum friction. So in the end, we can interpret why this control can do better than this, for example, trapezoidal one that was previously proposed. And since I was mentioning trade-offs earlier, we computed here the trade-off between the cooling power and the efficiency. So here, each dot is a different cycle, so different optimization. And up here, we have solutions that have high power, as you can see on the y-axis, but low efficiency. And as we move along this so-called Pareto front, we have solutions that have lower power, but in exchange, they have a better efficiency. And this is, for example, how these cycles look. So if you're interested in power, so in points up here, we find these pretty fast cycles. And as we shift our interest to efficiency, we have cycles that are slower and slower. And to conclude, we also applied this to the case of a particle trapped in a harmonic potential. And our control here is the confinement of the particle, or if you want, the frequency of the quantum harmonic oscillator. And again, here we study the system in this case as a heat engine. And here again, we show the Pareto front, so the power, the average power of the system versus the efficiency. And here we have solutions that have high power but low efficiency. And as we move along this front, we have solutions with slower power but with high efficiency. And these are the cycles that we found. So here we compare to what was proposed again in literature, which are these Otto cycles, that in this representation, let's say control as a function of time, they look like these dashed lines, or these trapezoidal lines. And we see that our method finds cycles that look remarkably similar. So they have a similar structure, a hot stroke, then a cold stroke, and also the period is roughly similar, but we have some additional features like this ramping of the control and these unitary strokes that allow us to have the same efficiency, but a higher power in this case. And we didn't bias our method in any way to find solutions with this type of structure. Okay, so yeah, to conclude, I briefly mentioned how we can use reinforcement learning to find cycles and optimal cycles in quantum heat engines and refrigerators. We've seen that they perform better compared to more intuitive strategies that have been proposed in literature. We also propose a model-free extension of the method, which means that we only give the agent information about the heat currents and no knowledge about the quantum state nor about the model. And in fact, those Pareto front I showed were actually found using this model-free method. We've also looked at a full multi-objective, let's say, optimization, including power fluctuations, and compared how this compares to the TURs. And we've recently also looked at a system beyond the weak coupling regime. And as further applications of machine learning, let's say still in quantum thermodynamics, we've looked at how to optimize the charging of a many-body quantum battery. And as future direction, we're working on including also quantum measurements and feedback into the optimization cycles. And yeah, perhaps it would be interesting also to go to many-body systems. And yeah, that was it. Thank you for listening.